you know what is file, you know what is execute, you know what is wait. But actually behind the screen, inside the kernel, what the kernel is doing, okay? And today we will talk about maybe a new concept to you, okay? You know that there's a process to run, and it has a running time at the end. How that time is structured, okay? So we have what we call user time, system time, and real time. Okay, so today we will talk about these three types. I think we can cover up to execute and fork, how the kernel deal with it. Okay, so let's start with what is the kernel. Okay, so what is the kernel? I never mentioned a bit. Okay, so you will see this picture a lot. By the time goes on, this blue part will be expanding, become bigger and bigger. Okay. So from a process point of view, this picture is a very good summary of the whole chapter. Okay? From a process, I mean even the whole course. Process, know that they have this. Okay? So kill the constant, the memory, global variable, local variable, and even static variable. Later on, I will tell you what is static variable. To give you a clue. Okay? Global variable is actually the same as static variable. Okay? So this bunch of things. So this bunch of things is a code that is written by you, can be seen. The code written by you, let's say get PID, you write the code, but the invocation body, the body of PID is actually hiding here. So the kernel, what is a kernel? Kernel is not a process. Okay, make sure that you remember this. You don't understand it, but remember this. Kernel is not a process. Kernel is a piece of code. Okay, a huge code. It can be compiled. It has its main function. It has its timer. It gets segmentation faults. Okay, yeah. Think about it. What happens if kernel gets segmentation faults? In a unique class, we will try. Don't worry, just reboot the machine. Right? Okay. So here is just a piece of code with some memory, holding structures, process structure, file system structure, memory pages. Okay. Caches, all things are put in what we call the kernel space. So we have kernel space memory, user space memory, kernel space code. Yeah, because you need to load the code in memory, right? Kernel space code, user space code. Okay. Usually, how you distinguish it? User space memory, user space code are generated by you. You write the program. You launch the program so that you create a memory. The kernel, you don't need to care. Once it's put up the machine, the one and only one kernel will appear in the system, hiding somewhere in this map. We call it system memory map. I just draw it by random. Okay, it may not be the bottom, may not be the top. Yeah, just an illustration. There is a piece of continuous system memory managed. System RAM, okay, like your RAM that you plug in, add together you have 16 GB, okay, and a part of it we allocated for a kernel, okay, approximately 1 GB, approximately. If your system don't have 1 GB, it will be smaller, okay. So that's it nowadays. Who is still using 1 GB system except your phone, okay? Yeah. If you have a laptop, it must go beyond 1 GB, okay. So this will reserve a space of 1 GB, loading the code, loading the structures for process, all the memory concerning the kernel. You know, remember, kernel is just a program, and it's a thing. So it needs memory to host all the thing. And this area is to host all the processes. Okay, you run a process, some part of it will allocate to your program, to your process. And this is just like a public place. This is a private place for computer. Okay, so let me write down some differences here. We have kernel space memory, kernel space. What happened to me? Okay, kernel space memory, user space memory. Okay, and they are storing different things, and there's no duplication, right? You can see this. They have its own data structure, and data structure won't export to user space. Okay, each part do its own job. And the more important thing is, yes, we access memory using code, right? You use code to access a piece of memory, right? You do assignment statement, you do your manual, you use pointer, okay? All are controlled by your code. And actually, the kernel code hiding here can access both areas. Ah, that's interesting. That means what? The kernel can suddenly give you more memory, or suddenly remove some of the memory without your consent. Okay, you say no, but no. One will say that you have this pure pocket money this year. Okay, you cannot say no. Okay, so this is your mother. Okay, you reduce your pocket money. No one will say no. You can only say I don't want to, and then you go something here. Okay, this is your problem. Okay, but how about the user space memory? A user space code. I mean, user space code cannot access kernel space memory. Cannot. But am I saying something wrong? Right, I can go get PID to get the PID. And I just said that the get PID is to call the code hiding here. So actually, what is the control? Hey, it's kind of difficult to understand. I call a function from the user space code, user space memory, user space code, and try to access kernel space. Now, this is something that usually people will get lost. This is the illustration. The illustration is like this, okay? So you are running a program, and that program contains a code that asks for a call or get PID. And get PID is a system call, okay? So the CPU originally is pointing to this code here, okay? Remember, it is from the CPU point of view. CPU point of view executing this part, accessing the memory that in this area, because your code cannot touch this area. So this is being rejected by default, okay? When you point to somewhere here, boom, segmentation faults. Okay? Now, what's next? Now this is the time that you call the get PID system call. What will happen? When you call it, it's as if you are jumping. Now, what is you? You are the CPU. The CPU, look at from the CPU point of view, okay? You are the CPU, you look at some code, okay? This is written by you. And suddenly you call a jump from your code to the kernel code. Okay, you are jumping from one code to another, and now you are inside this area. I said that kernel code can touch kernel space memory. So because we jump from this area to this area, you now is touching kernel space memory, but using kernel space code. Okay, so that means what? That means your action is being monitored and controlled. You call for get PID, you can only get the PID. You call for malloc, you can only get the memory, but not anything else, okay? Now here, after it's finished your call, let's say the get PID is returned to the PID, inside here is contained a function. Let's say the function is just called get PID system call. It return out. When it return, it automatically go back to your own code, okay? So this is the control from the CPU point of view. And from your process point of view, your process don't know about it. Your process say that, oh, I call a function, and suddenly, boom, jump into the kernel space memory. Your process don't know what is going on because the CPU don't look at you anymore. The CPU look at here, finish the context that you want to execute, and come back. Okay? So from your code, as if you're calling a function. But actually, from a CPU point of view, you're jumping from one space to another, and through this code, you can touch any kernel space memory. Okay, so what is the difference between this and use normal function call? No difference, okay? And yeah, this is the system call in kernel. Now, why I make this so explicit and spend 10 minutes to talk about it? Because we have to talk about one thing. It's about this time graph. So what's this time graph? This time graph is generated from the CPU point of view. The CPU running your code, I give it the color orange. The CPU running kernel code, I give it the color blue. Okay, so I always use this blue to represent the kernel. Okay, so when you look at here, usually I will say that, let's say, imagine you are running your, how many of you didn't take data structure? Yeah, if you don't take data structure, okay, you imagine that you are doing a while loop, okay? Let's say you're running a data structure assignment. Data structure assignment usually manipulate memory, right? Manipulate memory, doing some sorting, doing some graph searching, so on and so forth, or a lonely for loop, okay, for loop, and go out, okay? Now, this is what we call user code. You write that, okay? And it usually don't call printf in the middle, right? No one doing the sorting and keep on printing the intermediate step, right? Stupid, okay? So you don't call printf, and here you will get this graph. During this time, a long period of CPU time is spending on your code. We call it user time. Okay, we call it user time serving your code. And let's say, imagine that after you do it, okay, the sorting, let's say you have finished sorting, you want to print the results. Let's say you print the result first, print sort done, okay, done now. Then it suddenly go to the blue zone. Why is that? Because you are calling printf. Printf is a touch hardware. Okay? So you suddenly jump to here, ask the kernel for a service, just print a line called done. Okay? Then here we will contribute another time and look at it from the CPU. The CPU, because you call printf, it suddenly jump from the user space to the kernel space. And it's what we call system time. Okay? System time is not a good thing. It's not a good thing. Usually we will minimize it. Later on I will tell you why. It's actually not difficult because system time usually involve hardware. Hardware is slower than memory. That's all. Okay? Now, how about another range? Maybe another range is now you're not really not here. I don't know where you find a floppy drive. Okay? How many of you know what's floppy drive? Okay? Yeah, good, quite good. We don't have any generation here. Yeah. For others, what is floppy? Floppy. Yeah, next time bring it here and let you dissect it. Okay. Yeah, I throw it away. Oh, shit. I threw it away. I only have the floppy left. Okay, let you take a look. So let's say going to the floppy. Floppy is a bad guy. Floppy is a bad guy because the device itself is small. Slow. Not small. Slow. Okay, it is slow. Then the system time will go up. Okay. Now, why it is so important to tell you about this? Because usually when you measure the performance of a program, okay, let's say you're doing ACM programming contest, it's always mentioned to you that hey, your program has to finish within a time. Then now you should ask the question, what time? Not AM or PM, okay? Yeah, what time is this? Close to 2 o'clock, okay? It's about user time, or system time, or user plus system time. Right, you should ask this question. And you don't know, okay? Because you don't know about it, so you don't ask, okay? Now, let's take a look. What happens if I alter a program to generate different combination of user time and system time? So this is a very simple program, and we have a command called time. Okay? The time command can show you when you execute a program, after it's stopped, it will show you 3 times. One is user time, the time spent on user code. System time, the time spent on the kernel. Last, the real time. Now the real time is hard to understand, okay? This is a bad example. 0, 0. Actually, the precision is not enough. So you cannot find a program that spends 0 time, right? It's because of the precision, but add together, the waiting time is more than 0. Later on, I'm going to show you a better example. Don't worry. Okay. The user time is the time that when you issue the command and you do fork and execute, right? You want to run the new process, fork and execute. Once you start the execute, it time it until the process stops. Understand? So it is a kind of hybrid thing, okay? It includes user time, it includes system time, it includes the time you wait for the floppy, it includes the time that you wait for scanf, okay? All times are included. So usually real time is much bigger than the sum of user and system. Now, let's try this. I have an example code called timeexample.c, and yesterday night I update my, the color is bad. Can I make it bigger? Good. Okay, so I update the code. If you didn't know how to use Git, okay? If you use Git pull, okay, Git pull, then you will get a new code. If you don't use Git, okay, download the zip again, okay? So I update the code, and it's inside the directory called chapter 2 part 2 here, okay? So this is chapter 2 part 2, and the example time example.c. Let me run it and later on show you the code. Time example. Hey, oh, I didn't make it. Right? Time example. So there are two modes of this program. The first mode, okay, use 0. That means that it will go through a loop. Okay, I run a loop, and the loop don't call any printf, just go through the loop. Second call is I do the loop, and while I'm iterating, I will call printf. Now let's take a look at the code structure. The code structure is I adopt your input. So there are many codes here. The core is here. The core is this part. Okay. So I loop for a long time. Okay. I loop for a long time and try to print things. Okay. If I set the printf equal to 1. Okay. I just print out something. I just make it into a strange code. I print a floating point, whatever things you want to print, okay? Just print things. Each iteration, print it out, okay? So let's try this first. The time command, you can try it together. Time example, I don't call any printf, okay? I don't call any printf, so what is the result? Look at the number of loops, okay? 1 million. 1 million in my Mac machines, you spend user time. That is the time that you use for on the loop itself and other code. And the system time is the time that I spend on the kernel, maybe including the let's say the main itself. When it returns, it will call the system call. And others, I don't have any system call. Yes, I don't have any system call. So I minimize the number of system call so that the system time is very small. And look at the real time. What is the real time? Is it bigger than the sum between the user and the system? So the reason is, okay, the reason is I have more than one process in the system. During that time period, I launch a process, and another process have to share the CPU with me. So I have to walk away for a while and then come back to the CPU. Okay? So it is the waiting time plus the real execution time. So for ACM programming contest or other programming contests, they won't calculate the real time. Okay? Because it depends on how busy your system is. And user time and system time never adopt to the status of your system. Because really executing your code, okay, for 10 lines, then with 10 lines time, 11 lines will be 11 time, 1 million call with 1 million call time, okay? It's independent of the waiting time that how many processes share in CPU with you. Understand this point? This is invariant. Invariant if you are looking at user plus system. Okay? Understand? Any people want to ask any questions about this point? This point is very important. You give the same code, give the same inputs, the time will be invariant. Okay? Good? Then what? Printf. Printf sucks. Look at the time now. Ooh. What happened? How can you compare? How can you explain the results? Yeah, wow, super busy, right? Previously, the significant digits start here. Yeah, it is 100 times. Okay? So what is said? What is the extra time? Now the real time, you understand, because you have to wait. You have to wait for all the input go to the device. So you know there incurs some penalty here. You have to wait. Now, what is this and this? It's actually the printf itself. You call it extra call, right? The printf is actually a library call. It goes through some manipulations and finally call the system call. So these two times will be very, very close together. And to my surprise, actually, the system time is more than the user time. Yeah, it's a little bit out of my expectation. Let me try again. This time is also more, okay? A little bit more than, I think that the system time will be smaller because, the format itself, the format is more complex, right? Should be more on the user part, okay? So this is the time. And now you understand that, hey, the more printf you call, the more stupid your program will become, the slower the program will become. So let me ask you this question. The question is on the lecture notes itself. This is the result of either comment or not comment this thing. Okay? Now, how about this two? Oh, no, sorry, not this two. This two is the comment and non-comment. How about this two? Wow. So understand this two, what is the difference? A difference in the output. Yeah, give you 1 minute, okay? Yes. Any difference in output? Yes, someone. Any output difference without time, the time of course will be some difference. The output should be the same, right? I look the number of times is here is 1 million. This is not 1 million, but divided by 5. But my output is 5 times more. Okay? So here is a very good example to tell you that your right, I call more printf call. No, my right, my right, okay. My right, I call more printf call. My left, fail printf call. Let's go. No. Let's try the slow first, huh? Okay, time it, and it'll print out something. Okay, so this is the slow version. Let me copy and paste it. Copy. Okay, paste it here. Okay, so remember this. This is the slow. Okay, so how about the fast? Fast is a print 5 times less. Okay, so this is fast. Not a big difference, huh? Not a big difference, okay? But you can see this is actually faster by a little bit, okay? So there are a set of rules if you understand, hey, I understand the more system call I call or the more functions that I call, I will make the program slower. So there are a set of, this is the example, some of no-nos, some of do's and don'ts, okay? Don't do this. Over a file, you use fgetc, reading 555. You may think that, it is nice, okay, because you don't know how to write it faster, right? Yeah. I wanted to add 555, okay, character by character. No, please don't do it, okay? You are generating many calls, okay? The suggestion or the recommendation is, this is harder, right? You create a block, let's say 4K. You read 4K memory from the file, put it in your buffer, you process it later. It will be much faster, okay? And this is something that you even find it harder to believe. Your, data structure class, okay, may tell you this. Do malloc and free is sexy, right? We are doing something flexible. Bullshit, okay? If you're running this code, okay, you keep on calling malloc and free over a fixed size of memory. You are doing stupid thing. Yeah, just like you're going to your mother. Hey mother, I want $100. take it and give to your father. Father, okay? Yeah. Then you both parents will want to kill you, okay? Because your mother will think that you will have less money, and the father, yeah, you understand, okay? So, yes, why are you doing that? Why don't you fix that buffer? Yeah, you declare a fixed buffer, even put it on a global variable zone. Put it with global. Yeah, you reduce the number of core. This time it's not about software reliability, software reliability, or code organization. It's about performance. Okay, I tried it. This example is not a fake example. I duplicate this experience from a GPA 4.0 student. Okay, I have a FYP several years ago. That guy is 4.0 for several semesters, and he crashed for good code and write this stuff. Okay, and my first expression is, and then of course I don't say bullshit, okay, and then please change it to believe me, okay. So at the beginning, he don't believe in me, okay. I said, hey, change it to a static array. Then after I change it, okay, so what he's writing, he's writing a file system driver, okay. That file system driver go through some tests, very slow. After change it, the improvement is 30% of speed, okay, because it's doing something stupid, okay. So the good GPA don't mean anything for me, because I understand it, okay. Yeah, this good student will also follow some people tell you, but here is a really interesting example. You can go home and try it, okay? Manual and free for 1 million times, okay? Then you will see how many extra time you will need it, okay? Do you have any experience over this kind of stupid thing? Do you have any experience? Okay, if you have, okay, remember it. Try to reduce the number of core from now on. Okay, have this kind of sense in your brain. Okay, so need any time for you to digest. Okay, this is a kind of a cultural shock here. Okay. Yeah, it's not just manual and free. It's also for Java sucks. Okay. C++. Okay. You create an object and destroy an object. Still the same thing. You keep on create, destroy. Why I said Java sucks? Okay. You knew it and the system just don't work. Okay. Yeah. Yeah. Java really sucks. Okay. So how about fork? Okay. Now we understand some part of the kernel. That a kernel has a piece of code, that's all. And to work with its own piece of memory. Now I will disclose to you what exactly fork is doing. Then we'll end this lecture. Okay? And next time we will talk about execute, wait, exit. After we know wait and exit, then we will understand how to produce a workable fork ball. Okay? So fork. Fork is really great. It's from a CPU point of view, let's say we have a CPU that have multiple cores, then you will see this graph from a CPU point of view. You are the orange guy, orange process, go through some execution, suddenly you call fork, you ask for the service from the kernel do something, and then you steal the green guy, but now you have a folder called, not green guy, sorry, orange guy, yeah. New folder called green guy, okay? Green, white folder is a guy, okay? Green process, okay? Yeah, yes, I always like that, okay? I always like to mix this, okay? And what happened in the kernel, okay? So whenever you see the blue color, it means that all happened within the kernel, and I don't know whether you believe it or not. Actually, inside the kernel, there is a double linked list. Okay, double linked list? Yeah, how many of you don't know what is double linked list? Yeah, drop this course, you still have to try. You still have a chance to do it, okay? Double linked is that? So there is double linked list. How to construct? You don't know, no problem, okay? Yeah, this course is not asking to re-implement anything, okay? You understand what it is enough. So, double linked list that inside the kernel, and it will host all the processes. At most, I have to update my slides, okay? I have to check the new limit, but the old limit of the number of processes is assigned the integer, assigned the short integer. So this is 32,000 something. Okay, the limit. So here, this, although this number limit seems unlimited, but the number of processes is limited actually. Now, let's say we have this list. Okay, when you call fork, you ask the kernel. You are 1, 2, 3, 4. Let's say you are 1, 2, 3, 4. You ask the kernel to duplicate yourself. So what is the exact meaning of duplicate yourself? Actually, this we call it process structure containing a set of useful information. It contains PID inside structure, running time, an array of open files. This array of open files is very interesting. Okay, you have an array, right? Array index 0, 1, 2, 3, 4, all the way down. When you open a file, it will occupy a slot, and I don't know whether you know it. Standard input, we usually call it a number 0. Okay, it's because in an array of open files, standard input is the first guy, 0. Standard output is 1. This array number 1 is standard output. Standard error is number 2. The first open file will be number 4. Number 3, sorry. What happened to me? Number 4, this is number 3, okay? Number 4, number 5, all the way up, okay? So there's an array of open files. Now, when you ask for duplication, all will be duplicated at the beginning, okay? So I said that this will be also duplicated, the array of open files. So one of the very important facts is actually you are sharing the same standard input, standard output, standard error with your parent process, right? When you call fork, the child process keep on pointing to where? To the same screen. It's getting input from where? From the same terminal, okay? So they are duplicated in this way, and then they will do some reset. We set the PID, we set the running time, this is preserved. Parent pointer, there's a parent pointer, but this parent pointer is just an illustration. It's just like this doubling list, but the reality is not, okay? So there is some pointer for you to update. Now this is on the kernel part. I said that the kernel code, fork is a piece of kernel code because fork is system call. Kernel code can manipulate user space, okay? So some horrible things will happen. The horrible thing is, this area is no longer blue, so this is, I usually change the color because I run out of color. Now I use a yellow, okay? So to imagine that this is a user space memory. The user space memory will be directly copied from the old copy. There's old copy, there's new copy, and now you understand, when you call fork, I said that you create a duplicate variables. Let's say you have a variable called results in a local variable zone of the main. Main is a function, so you have a local variable, and you put the local variable called results here. You duplicate another results carrying previous value. It is because of this. Doing an identical copy, and some people, I remember it's last week. Okay, he asked me, okay, let's say I have pointer, okay, point to some address, and where is that pointer will be copied? Yes. Because this pointer, let's say it pointed somewhere, but you cannot point outside to anywhere. You're just jailed within this area. You can point to your own local variable. You can point to your own malloc zone. Yes. With the copy, you are copying this pointing relationship. Okay? So all pieces of even 1 bit will be copied. Then the last step, return value. The return value. The two processes now is ready to return, and they will give you different return value. This guy will store, that seems to be hard code, right? Hard coding that, oh, my child process is now 1, 2, 3, 5. Now I put that 1, 2, 3, 5 here, and because I'm a child process, so my return value is 0. So this is the inner working of fork. Okay? So now you understand that, hey, how about destroy a process? Yeah, destroy a process, yeah, remove it from the linked list, okay? Or how about other changes to the process? Let's say that I want to retrieve the PID. Very easy. It's actually getting this PID from this structure. Okay? So this structure is contain many things. Later on, we will keep on telling you more. Okay? This is the thing that about 0, 1, 2, and 3 and beyond about the array of open files. Okay, so remember it's being duplicated, and the one of syndrome is these three guys will also be being copied. Okay, so any question you want to ask? Any question you want to ask? If no,
yes.
I forgot to put down this file. Yes, where?
If I call time, will the
Time.
process be counted in the user time?
Very good questions. No. Time is a special call. It only counts the number of child process from the calling shell. The calling shell fork a process, and the time only calculate the child process, not grandchild. Yeah, your child process create 1 million child process, it doesn't count. Okay, it's only count the first layer of the child process. Okay, I forgot to put down this code. Okay, I remember I will put it down in the GitHub. Okay, actually I write an example for you to understand what is the meaning of duplicating the open file. What is the meaning here? It means that, let's say I have a process, okay, originally is writing the file, open in mode run. After you call fork, yeah, the same file can be controlled by two different processes. Okay, can be controlled by two different processes and pointing to the same file. Yeah, don't tell me that, after fork, this file will be forked also. Yeah, then you tell me you call fork, you duplicate another backbone. Okay. Yeah. Right? Yeah, if that's the case, I want that fork call. Yeah, give me more backbone. Okay. Yeah, no, this is not possible, right? So in the design, okay, this part will not be duplicated. Okay? And I forgot to put down this example. Okay? So I will remember tonight, put it down, and then you can try to modify it. After fork is actually being shared. Alright? So I think this time is up. Next time we will talk about execute, waits, exit. Then exit is a very important call. Then we will go to look at what is solving. And I will bring my EPC to LSK and demonstrate pop-up. Two different forms of pop-up. And if you are, I think this is the end of the end job period. Let me stop the recording.